Okay, hi guys, Mr. Rocco. I hope you're having a good weekend. This is going to be the week of November 9th. We have Veterans Day coming up, so make sure you thank a veteran. This Wednesday is Veterans Day. Also, for work this week, you have a test on Topic 2. That is going to be the assignment. The link will be on Canvas. It's going to take you to another site called Castle Learning. Again, I put instructions in my announcement section on my Canvas page, so please read that set of instructions, how to set up an account, and then you're going to take that test on Castle Learning. The test is 37 questions. 32 of them are multiple choice, 5 are short answer. You don't have to do it in one sitting. You can do, blocks of 10 each day, but the test must be done by 3 p.m. on Friday. If you don't do it by 3 p.m. Friday, the window's going to lock and you won't be able to finish the test, and that's it for that. You may use your reference table. You should use your reference table always when you take a test. You might need a calculator, so have that handy, and that'll be the test. On top of that, there'll be, I was going to make one video to start on astronomy. I'm going to be making 2 videos. They won't be hopefully too long. A lot of it's YouTube clips. And there'll be an assignment that goes with it, the Big Bang worksheet. So you have videos on the universe to watch and the Big Bang worksheet, and you have a test. On top of that, you also have your lab. This will be a topographic map lab. Should be pretty easy. I will post that, and again, remember we have 2 weeks per lab, so it won't be due this Friday. It'll be due, Friday, November 20th. On the 20th, the next lab will be due. Also remember that the first quarter ends this Friday, coming up the 13th. If you owe work, you must get any missing assignments in by Friday. Some of you need to make sure you get all those assignments in, or you might not pass the first quarter. Most of you are doing well, but some of you have to really step it up this week and get those assignments in. All right, so let me start with, this is how the universe began. So this is a short YouTube clip on that.
Explain its particles to the largest galaxies, to the very existence of space, time, and life. But how did it all begin? The origin of the universe is the origin of everything. Multiple scientific theories, plus creation myths from around the world, have tried to explain its mysterious genesis. However, the most widely accepted explanation is the Big Bang Theory. The Big Bang Theory states that the universe began as a hot and infinitely dense point. Only a few millimeters wide, it was similar to a supercharged black hole. About 13.7 billion years ago, this tiny singularity violently exploded. And it is from this explosion, this bang, that all matter, energy, space, and time were created. What happened next were 2 major stages of the universe's evolution. Called the radiation and matter eras, they're defined by key events that helped shape the universe. First came the radiation era, named for the dominance of radiation right after the Big Bang. This era is made of smaller stages, called epochs, that occurred within the universe's first tens of thousands of years. The earliest is the Planck epoch. No matter existed in the universe at this time, only energy and the ancestor to the 4 forces of nature, the superforce. At the end of this stage, however, a key event occurred in which gravity split away from the superforce. Next came the Grand Unification epoch, named for the 3 remaining unified forces of nature. This epoch ended when one of those forces, called strong or strong nuclear, broke away. Then, the inflationary epoch began, during which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of a grapefruit. The universe at this time was piping hot, and it churned with electrons, quarks, and other particles. Then came the electroweak epoch, when the last two forces, electromagnetic and weak, finally split off. During the next stage, the quark epoch, all of the universe's ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then, in the Hadron epoch, the universe cooled down enough for quarks to bind together and form protons and neutrons. In the lepton and nuclear epochs, the radiation era's last two stages, the protons and neutrons underwent a significant change. They fused and created nuclei. And in doing so, they created the first chemical element in the universe, helium. The universe's new ability to form elements, the building blocks of matter, cued the matter era. Much as the name suggests, the matter era is defined by the presence and predominance of matter in the universe. It features three epochs that span billions of years, the vast majority of the universe's lifespan, and includes the present day. The first was the atomic epoch. In this stage, the universe's temperature cooled down enough for electrons to attach to nuclei for the first time. Called recombination, this process helped create the universe's second element, hydrogen. This hydrogen, along with helium atoms, dotted the universe with atomic clouds. Within the clouds, small pockets of gas may have had enough gravity to cause atoms to collect. These clusters of atoms, formed during the galactic epoch, became the seedlings of galaxies. Nestled inside those galaxies, stars began to form. And in doing so, they cued the latest and current stage of the universe's development, the stellar epoch. The formation of stars then caused a tremendous ripple effect and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turn, those elements became the building blocks for planets, moons, life, everything we see today. This ecosystem of everything was only possible because of the many stages in the universe's development. While countless questions about the origins of our universe remain, it's only a matter of time for some long-sought answers to emerge.
Okay, so let's move on here. So as the video talked about, it said 13.7. So in that general area, roughly, is believed to be the universe, 13.7, 13.8 billion years old. There was some discrepancy in the beginning of this whole idea of the Big Bang. It was 10 billion. Then there's been some astronomers put it at 15 billion. But right now, currently in the year 2020, they're at about 13.7, 13.8 billion. Now, that's the universe. That's not our sun and our solar system. You heard in the video, they talked about stellar epoch. So a stellar epoch, stellar meaning stars. And so our sun being one star in our Milky Way galaxy, our sun, didn't form until about 4.6 billion years ago. So that will come up sometimes on a test. The universe is 13.7, 13.8 billion, but our sun, our solar system, Earth, and our planets are only 4.6. So there was about roughly, 9 billion years if you do the math and subtract those numbers. There was 9 billion years from the time the universe began with the Big Bang to the time our sun and our solar system formed. Okay, so this video talked about this. Big Bang, all matter started as this minuscule mass of material. It wasn't really a bang, it was more of an expansion, as the woman talked about. And again, the first two elements to form were helium and hydrogen, which happen to be the two elements that make up stars. So your stars are made of hydrogens and heliums. And that's something we'll talk about in a little bit here. This was supposed to be a joke, so if you turn on Fox News from time to time, they always do these Fox News alerts when there's some breaking news. So, explosion rocks empty space. Ha ha ha. The actual Big Bang theory goes back to a gentleman in 1929. His name was Edwin Hubble, which you've probably heard the name Hubble before. That is the Hubble telescope that they named after Edwin Hubble in honor of the work that he did. So he proposed this Big Bang. So it says Hubble made the observation that the universe is continuously expanding. He discovers that a galaxy's velocity, a speed of a galaxy, right, is proportional to its distance. Meaning galaxies that are twice as far from us move twice as fast, right? Galaxies that are 3 times further away move 3 times faster, etc. He used an idea, it was called the raisin bread theory, raisin bread analogy, I guess. So if you think of let's say you're going to make raisin bread, you're going to bake a loaf of raisin bread. You have the dough, and you put the raisins in the dough. The dough represents the universe. The raisins represent galaxies. So you're going to put that dough, the universe, in the oven to bake it. As it bakes, what happens? The bread expands, right? The dough, I should say. The dough will expand to make the bread, but the raisins don't grow any bigger. They just move further away from each other. So that's Hubble's idea there with this raisin bread idea, is that, yes, the universe is expanding, right? The galaxies are moving away from each other in all directions, but they're not getting larger, right? Our galaxy is only so big. It only has so many stars in it. It's not going to grow. It's just the universe itself, the space between galaxies growing. It says another consequence is that the universe is expanding in every direction, again, like raisin bread. This observation means that it has taken every galaxy the same amount of time to move from a common starting point to its current position. Just as Big Bang provides the foundation of the universe, Hubble's observations provided the foundation for the Big Bang. And so I have another YouTube clip, so let me play that for you now.
For centuries, the fact that we can discover things about the universe has really been something of a mystery. Why would beings like ourselves be able to discover a universe like this? Why is what we think about the universe, why would it correspond to the way things really are?
Our ability to discern and understand the universe is a fundamental part of what makes the universe tick, so that we're linked into it. This isn't just a sort of an accident, a trivial little byproduct. It is something that is linked to the great cosmic scheme of things. Now, I've no idea how that linkage works, why it's there, or anything of that sort, but I'm very, very struck by the fact that we can understand the universe in such exquisite detail and at such a deep level.
The spectacular progress of modern astronomy and physics is the product of a universe accessible to the human eye and mind. It is a universe governed by laws and forces that literally hold our planet Earth and the entire cosmos together, and are finely calibrated to allow for both complex life and scientific discovery.
If you didn't have something like gravity that pulled matter together, you would never get planets, you wouldn't get stars, you wouldn't get any complex organisms. If you didn't have the strong nuclear force, there would be nothing to hold protons and neutrons together in the nucleus. And so you wouldn't have any atoms, so no chemistry. If you didn't have the electromagnetic force, you would have no bonding between chemicals. You would have no light, and the list goes on. So you need all these sorts of fundamental principles have to be in place in order for life to occur. Wipe out one of those principles, wipe out one of those laws, no life.
During the past 40 years, scientists have determined the relative strengths of each of these primary laws and forces. These strengths are so critically balanced, they are often described as being finely tuned.
If you're to take the basic fundamental constants of nature and you were to change these even slightly, or you were to pick their values at random, you would almost never get a universe that would be habitable in any sort of way. That is, you couldn't have galaxies, you couldn't have planets, you couldn't have complex biological organisms if these fundamental constants were even slightly different, slightly stronger, slightly weaker than they actually are in this universe. That's the idea of fine-tuning.
To better appreciate this concept, imagine a machine able to control the strengths of each of the physical constants. If you changed, even slightly from its current setting, the strength of any one of these fundamental forces, such as gravity, the impact on complex life would be catastrophic.
If you increased it by a little bit, no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
Now, this is one of a long list of properties in underlying physics that seem to be prerequisites for a universe with life. For example, the strengths of the other forces are all important, the masses of the various subatomic particles. If all of these things were even a little bit different, then life, certainly life as we know it, could not exist.
These forces and constants are another example of the correlation between life and discovery. For not only are they finely tuned for our existence, they can also be understood.
It's remarkable how well the laws work, and not only that, it's remarkable how simple they are. And that also is related to the discoverability of the laws.
Albert Einstein wrote, "I have deep faith that the principles of the universe will be both beautiful and simple." For nearly 400 years, scientists have discovered an elegant simplicity in the mathematical equations that express and unlock the laws of the cosmos.
It's been said that many of the most important theories in theoretical physics can be written on a single sheet of paper. And this, I think, ought to be considered surprising, that such a simple formula or equation could have such far-reaching applications to a very complicated and very large universe.
What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
Most scientists just take it for granted that the world is both ordered and intelligible. And the intelligible part I find really quite extraordinary, because it's one thing to accept that the universe is ordered, but ordered in a way that human beings are capable of understanding is an extraordinary thing. And so the question naturally arises, what is the explanation for that?
Many who have pondered this mystery of an intelligible universe argue that it cannot be easily explained away.
From naturalistic assumptions, you would not expect the universe to be understandable by human reason. After all, within the standard naturalistic story, human reason was developed to be able to hunt prey, get around in the everyday world, attract mates.
We have certain skills, for example, we can jump streams and catch falling apples and so on, which are necessary to getting by in the world. But why is it that we also have the ability to discern, for example, what's going on inside atoms or inside black holes? These are completely outside the domain of everyday experience, totally surplus to requirements, not at all necessary for good Darwinian survival.
The discoverability of the universe is something we didn't need for our existence. It's something additional to it. It seems then that whatever the source of the universe is, it intended that it contain observers who can discover.
Okay. There is another theory out there besides Big Bang. This almost goes in the opposite direction. So Big Bang says everything was, in that millimeter size and expanded rapidly outward. This takes it the other way. It's called the nebular theory. A nebula, which you should know, is just a huge cloud of gas and dust. And so that's out there in the universe, kind of spread out, covering hundreds of millions of miles. And then what would happen is slowly that force of gravity, as they were just talking about these four fundamental forces, the force of gravity would start to pull these gases and dust together, starting a slow rotation that would trigger the formation of stars and galaxies. And that's called the nebula theory. So it's almost the opposite. Instead of everything starting in one single little clump and going outward, this takes everything that starts out and brings it back in. The one thing you should take away from this slide right here is this one right here. Our star, as all stars, but our sun, which is a star, the fuel that makes it burn, the fuel that makes it, gives it, creates the energy, is called hydrogen. Hydrogen goes through a process called nuclear fusion. That you do have to know. Comes up on a Regents almost every year. It'll definitely be on your next test. So fusion is taking atoms and combining them. So if you have a hydrogen here and you have a hydrogen here, they're going to smack together. And this happens at a crazy rate. Billions and billions of tons of hydrogen are smacking together in our star every second. Every second they're smacking together. When they do, that creates energy. That's that light that we see. And it also produces helium. The light or energy plus He, helium. And so our star is going through this process, nuclear fusion, as all stars are. So when that comes up on the test, they'll say, what is the process that stars use to make energy? It's called nuclear fusion. Don't confuse that with what's called fission. Fission is splitting of an atom. So I would take, let's say, one of these hydrogens and split it into two more hydrogens. That's cutting it. That's the opposite. So I'm not doing that. I'm actually taking two different hydrogens, smacking them together to fuse them together. And that's the energy there. Our sun. So these are the steps that astronomers believe will happen to our sun as our sun dies. Right? Stars go through a life cycle just like we do. And so they're born, they live, they die. You might say, hey, Mr. Rocco, how do they know how our sun's going to do this? Just from observation of other stars. So out there in the universe, of course, there's billions and billions and billions and billions of stars. And so looking at other stars the same size as our sun and the same properties, they're able to determine roughly what our sun's going to do. And so I'm going to show you this video here that talks about our sun.
Like all stars in the universe, the sun is not immortal. The sun was born 4.57 billion years ago. It survives by burning 600 million tons of hydrogen atoms into helium atoms in its core every second. However, there is only a finite amount of hydrogen in the core of the sun. For the next 4 billion years, the sun will continue to fuse hydrogen to make helium. As more helium builds up, the core will shrink. As a result, nuclear fusion reactions accelerate. Faster fusion means more energy output. In 3.5 billion years, the sun will shine 40% brighter than today. At this point, Earth's oceans will boil, and the ice caps will permanently melt. All the moisture in the atmosphere will be lost. Life will not likely survive, and Earth will become brutally hot and dry, like Venus. After that, the situation gets worse. 5.4 billion years from now, the sun will exhaust all hydrogen in its core. The core will heat up and get extremely dense, but the sun's outer layer will expand a lot. It could expand big enough to swallow Mercury, Venus, and maybe even Earth. Even if it doesn't grow as far as the Earth, high temperatures will completely burn our planet. Once the sun has emptied its fuel reserves, it will become unstable, and as a result, it will begin to pulse. Each pulse will remove more of the sun's mass until all that's left is a cool, dense core. This core is called a white dwarf. The sun will spend the rest of its days as a white dwarf, slowly cooling and dimming as time passes. By this point, Earth will be completely inhospitable.
Okay. scary stuff. So as it talked about, the core, right, will get squeezed. The outer shell over time is going to slowly expand. At that point, that's when it's going to burn up Mercury, Venus. It's kind of, all bets are kind of 50-50 on that, whether it'll swallow up Earth. But even if it doesn't, the outer shell doesn't hit the Earth, it'll definitely burn us up. And then, like it said, the core is going to completely collapse and become what's called a white dwarf. It'll just be super hot and super dense, but very, very small. Won't matter at this point because Earth's gone. Slowly over time, it will go to a black dwarf. A black dwarf would just be... there's some energy left. You wouldn't even be able to see it because it's black, obviously, against the background of the universe, but it's just basically fading. It'll kind of slowly fade away, is basically what's going to happen. Now, this isn't the most violent way that stars go out, and that's because our sun is not the biggest star out there by far, and it's not the smallest. We're kind of average size compared to the other stars. And so this is a chart. We're going to come back and look at this again. I have some assignments on this. This is called the H-R diagram, which stands for two astronomers that came up with it. It's called Hertzsprung Russell. So Hertzsprung and Russell came up with this chart, which basically shows you where stars sit on the chart as far as a couple of things. Temperature, which is on the x-axis. Luminosity. Luminosity has to do with brightness, and excuse me, it says it over here. The rate at which a star emits, which means gives off energy, relative to the sun. Our sun is right here, right next to Alpha Centauri, which is very similar to our sun. So our sun has a luminosity, if you go over to the left, of 1. So they give our sun a value of 1 on the luminosity scale. Stars that are above are brighter and also much, much more massive. So way up here at the top, there's a group of stars called the giants and the supergiants. Here's the supergiants. These guys are 100 to 200 million times... that's the age. But they're much more bigger, and they're much, much brighter. So if you look at, like, for example, this guy's Spica. All right, Spica, if you come across, that's like... I don't know, 30, 40,000, 50,000. So that means Spica is about 50,000 times brighter than our sun. Polaris. We talked about Polaris, right? The North Star used for latitude. Here's Polaris. Polaris sits in what's called the giants, which are also big stars up here too. If you take this star, that little plus next to Polaris, and come way over here to the left, you're looking at 2,000 or 3,000 times. So that means Polaris is 2,000 to 3,000 times more luminous, giving off a lot more brightness compared to our sun. These numbers over here, all right, that's their age, or how long they live. So our sun, right here, with an average size luminosity of 1, that's the average lifespan of a star like our sun. They live for about 10 billion years. So our sun right now is 4.6, which means we have about another, 5.4 billion years to go. So we're almost halfway. Our sun is like in its midlife crisis. It's about halfway through its life cycle. The rule of thumb is the bigger the star, the more hydrogen it's burning up. Remember the process that I talked about, fusion, smacking hydrogens together? So bigger stars like these supergiants and these giants, they're going to burn through their hydrogen a lot quicker. Fusion is happening much, much, much greater, faster rate. They don't live as long. So our sun lives for about 10 billion years. These stars only make it about 100 to 200 million, which is obviously a lot less than 10 billion. So they live shorter time. And then down here you have the dwarf stars. So the dwarfs, they don't burn up their hydrogen quickly. It's a nice slow process, and so they last a lot longer. So our sun, 10 billion, these guys will live 100 to 200 billion years. So 10 to 20 times longer than our sun. Some of these guys, Proxima Centauri, Barnard Star, Procyon b, these are some of your dwarfs. Another thing you want to look at is surface temperature. So the temperature will affect the color. So our sun, which is right here, if you go now, instead of going across for luminosity, has a luminosity of 1. If you go down to the x-axis and come straight down like this, you can see our sun is yellow. That's why in kindergarten class, right, you used a yellow crayon, hopefully, to color our sun. It has a yellow color, surface color to it. Temperature-wise, these are in Kelvin. But you have to be very careful. Most graphs, right, you start in this corner over here and it goes higher as you go to the right on the x-axis. This actually works the other way. The higher numbers over here, see that 30,000, and then it gets lower as you go to the right. So just be very careful with this when you have to read the temperature. So you see here's 30,000, then it gets lower, 20,000, 10,000, 8, 6,000, 4,000, 3,000, 2,000. So they'll ask a question on the regions. They'll say, what is the approximate surface temperature of our sun? Well, if you come from that little plus and go straight down, a lot of kids will say, oh, it's above 6,000 degrees. But remember, getting lower as you go right. So it's not above 6,000. It's actually below 6,000. This line, let me use a different color here. This is 4,000. This is 5,000. This is 6,000. So we're sitting at, 5,500, 5,600, maybe even 50. That wasn't quite a good straight line. I drew like 5,700, I think, is usually the number they'll put on a Regents question. So that's that's surface temperature. That's not inside. If you go to the core of the sun, it's like 20 million degrees, something like that. It's millions of millions. But the surface is 5,700. Hot stars versus cold stars. This is where faucets are actually backwards. I believe in some European countries, I haven't been to Europe, maybe some of you have, but some European countries, the cold water is the red faucet, and the hot water is the blue faucet, which is the correct way actually to draw to make faucets. And that's because if you think of a flame, all right, let's say you got a flame here on a candle, the red is actually cooler. If you take like a propane torch or something like that, there's a blue part, really dark blue in the middle there. That's actually the hottest part of the flame, is the blue. And so blue stars are going to be the hottest stars. Red stars are going to be the coldest stars. And then everything in between, orange, yellow, white, blue/white. So it's actually reverse of faucets. So in this case, you can't think, oh, blue means cold water. No, blue actually means hot stars. Or red means hot water on my faucet. Yes, but in World of Stars, red means cold stars. So your coldest, smallest star would be something like Proxima Centauri down here in the bottom right. It's going to be what they call a red dwarf. Red dwarf. White dwarfs over here because there's the color white. So they're going to be red dwarfs. Your hottest and your biggest star is in the opposite corner up here, Spica. Spica is not only a supergiant, but it's a blue. So you come up and you come across like that. And so it's a blue supergiant. So Proxima Centauri is your coolest and smallest star, and Spica is one of your biggest and hottest stars. And that's how you read this chart. There's also another part here, life cycles. So our sun is technically still in the early stage. Any of these stars, which is where a lot of stars are, you see right in this section, it says main sequence and it says early stage. So these main sequence stars, including our sun, Alpha Centauri, Sirius, they're all still in the early stage. When our sun starts to go through that dying process that last video I showed you talked about, it's actually going to jump around on the chart. It's going to go up to a red giant. Remember, the outer shell is going to expand. So it's going to leave the main sequence. It's going to go this way. It's going to head toward the northeast, and it's going to end up over here with this group, Aldebaran and Pollux. It's going to be a red giant. After that, when that outer shell, remember the video said it's going to be a white dwarf, it's going to drop down to here. And you can actually see on the chart, it tells you early stage, intermediate stage, right? That's middle. And then white dwarf is late stage. So we're going to go from here to here to here. We're going to kind of zigzag across this chart as we go through the dying process. This poster just showed a picture. It was a poster. I think I turned it into a picture. Anyway, it shows our star. Our sun is like right down here where I put that arrow. So this will be our situation here. Sun, red giant, nebula, white dwarf at the end there. The big guys go out actually with a bang. So those big stars, let me go back, these guys, the supergiants and the giants, any of these stars up in this section, because they're burning up their hydrogen quicker, when they die, they go out with a big explosion, what's called a supernova, which are these bright explosions in the sky. Or their core will collapse down to become a black hole. Some of them, not all of them. Some of them. So our sun won't be a black hole. Our sun won't go out with a supernova. Doesn't have enough energy. Doesn't have enough mass, I should say, and so it won't go out with a big bang like that. But these guys will. The supergiants go out with the giants, I should say. Supergiants go out with the supernova and the black hole. Skip that, and I'm gonna stop there. That's gonna be the first video. I'm gonna make another video that talks about how do we know. There's some clues. How do we know that the Big Bang actually happened? So that'll be in the next video. Okay. And that's it. Thank you.